Hello, so I'm going to do a problem here from 5.4, and I'll try to explain some things in the book as well as they're coming about here. So here we're talking about this very powerful method, and very important thing actually we'll see as we go through this chapter, this idea of the eigenvalue method for homogeneous systems. So in a nutshell, here's a problem that I'll do. Well, let's suppose, okay, here's the general setup. Suppose we have a system of equations. Well, we can translate that into a system where we think of X as an n by 1 matrix, A is an n by n matrix, right? And the derivative of X is an n by 1 matrix. So the idea is that we try to choose a trial solution right here of the differential equation. And what you're seeing here is if I take the derivative of this, I get this lambda v e to the lambda t, where, of course, v is an n by 1 matrix, right? And here we have this. This is equal to this. That's just plugging it in. And what we get is this fact that we need 0 to be equal to this expression right here. And so, in fact, this is the equation. We need that, well, 0 is already there, is equal to the matrix A minus lambda times the identity, the n by n identity matrix, applied to V, we need to get 0, okay? So we learned that you can find non-trivial solutions. This goes way back, maybe in an algebra class, where I think we talked a bit about this. If you have a matrix, you take the determinant and you get 0, okay? So we get non-trivial solutions if and only if this determinant is 0. Where what we call this lambda, okay, this is a number, and this is called an eigenvalue, and V is an eigenvector. This should be reminiscent of some things we had covered in the past. Except here we have a finite dimensional system. All right, and V is not 0, and in fact, if in fact we notice that A of V equals lambda V. Okay, so moving along here. If V is an eigenvector associated with lambda, then it turns out that the good news is that this represents is a non-trivial solution of the differential equation, and that's what we're going to use to solve do this example. So here's this is example 10. I'll be doing a few other examples in later videos, but we're going to use this technique to do this number 10, and I'll just sort of read it here. So what we want to do is we want to apply this technique, right, this eigenvalue method for this section to find the general solution of the given system. Okay, it says if initial values are given, find the corresponding particular solution. And this is for each problem, use a computer system or graphical calculator to construct a direction field, okay, and typical solution curve for the given system. So I will do all of this. Okay. So here we go. All right, so we start off with our system here as indicated in question 10. So we were given this system of equations. We want x1 prime to be this, x2 prime to be this, and here I'm translating it into a system of equations expressed in sort of matrix form, right? So we have a prime is equal to a times x, right? Where let me show you how this happens here. So watch this on the side we have. So x in this example is equal to this vector x1, x2, right? A is the matrix. Well, I have it written there. Oh, it's written right there. Okay, crazy, right? And then the x prime, when we differentiate, we know we just take the derivative of the components x1 prime and x2 prime. Okay? All right, fine. So the first thing we need to do is to find the eigenvalues of the matrix A minus lambda I. So we do that by writing down what that is, and then setting the determinant equal to 0. Doing that, we find that we get, in this case, we get these two eigen values, but they're both complex. So we do get distinct, but they're complex. So in this case, let's now try to find the eigenvectors and hope to solve our system of equations. So what we do, here's the punchline. You see, since this is a complex number, so we have to actually consider the eigenvector v equal to this a over b to have complex entries for a and b. Okay, so I'll sort of run through that. In other words, we must consider, you can actually try to solve that without considering this, and it's not very fruitful. So if you let a be equal to x1 plus y1i, here I'm allowing x1 is not the x1 from above, so this is very bad notation. I'm just using sort of x1 and is not this x1. It's just let's say it's a local variable for those of you that are into computer science. So this x1 doesn't have to do with the x1 up there. And b is this x2. X sub 2 plus y sub 2i. Okay, then we write down what we have to solve. We have to try to solve this homogeneous equation. Well, what you notice is that in doing that, you write down the equations that have to be satisfied. And what you arrive at are these two equations. Simplifying those equations, what you notice is that the only way that this can be zero is if all four of these equations are zero. In other words, I need the real and imaginary part of the to be zero. I need also, as I've written here, I can then express that as a matrix equation. In other words, notice I have this. Here's my minus x3. Right? I'm sorry. Minus 3 times x1, minus 3 times y1, minus 2 times x2. That has to be 0. That's what's reflected here. See, here's my minus 3, minus 2, minus 1. And that would be multiplied when you do matrix multiplication, as you know from your algebra class. That's x1 times minus 3, y1 times minus 2. And okay, so this being 0, okay, is what gives us this first entry in this matrix. Now let's see, which one did I do next? I believe, okay, let's look at this one. This must also be 0. And that comes from here. We go. You see there's our 3x1 minus 3y1 minus 2y2, and then there's 0 for the coefficient of x2. Similarly, if you look at this equation, this must be 0 inside of here. That leads, what does that do? Oh, here we go. That leads to which one? Okay, we have 3x2, that's right here, minus 3y2, that's right, gives that minus 3 there, plus 9x1, that puts a 9 there and a 0 there. Okay, so that worked out. And then finally here, we are faced with, what do we have here? 3x2, so that's this 3, 3y2, that's this one, and plus 9y1 is this one. Okay, so we get this system of equations in four equations and 4 unknowns that we have to try to find a non-trivial solution to, and this can be done. It's a nice process of doing this row reduction, which you've more than likely seen in an algebra class or not. Or you can actually take and use the services of a very nice. I'm going to tell you some little trick that I did here. So using Wolfram Alpha, I don't know if you've had experience with that. I didn't want to actually deal with this equation, so I went to Wolfram Alpha. Let me see if I can find that thing here. Hold on, and you can. Let's see what we have here. Where am I? There's transformations, Corman. No, that's all different stuff. Okay, I can't find it. Well, I use Wolfram Alpha. You can type that into the internet, and it actually will solve this system for you. And we get these equations, okay? You can do it by hand, too, but I was just way too lazy today. So you get these two equations that result that give the relationships between the x's and the y's. So then you have to just sort of find one eigenvector, because we'll have an infinite number, in fact, an entire, at least one-dimensional linear space of eigenvectors associated with each eigenvalue. So we just need to find one to solve the system of equations. So here's why I pick x1 equal to 1, and you can plug that in there, and you plug that in right here, that will then give you, okay, you get this equation, you get these two equations, right? And then you can pick another one. Let's just choose y2 equal to 3, which gives you these equations. Then you can read off your solution. So by choosing those two, x1 and y1, we finally get these two. There's our a and there's our b that we find to make up our eigenvector. Okay, so therefore, sort of wrapping it all together and putting it all together, here's our solution that we get. We get x is equal to this one right here, just our vector, eigenvector, times e to the minus 3it. And now using de Morvier's formula for e to the 3it, we get this line. Okay, and then we can use, multiply that scalar into that vector to get this. Okay, and I'm just simplifying here, and finally, what we realize is that if we have a solution, and this is a beautiful thing about going into the complex numbers, is that if you have a solution of a complex system, right, then the real and imaginary parts turn out to be solutions. You can verify this. Are solutions of the real equations, right? Are real solutions, and that assumes that the coefficients are real, and a couple of assumptions, but everything that we're operating under in this class. Okay, so then the general solution we can unravel from that of this differential equation is given by the following. We then, in fact, can take scalar multiples, C1 and C2, of our solutions that arise up here. All right? So we get finally that this is the general solution of the matrix equation. And then finally, unraveling it even further, we find the general solution to our system, our system of equations right here. So we find that x1 is some constant c1 plus c2 times the sine of 3t plus c2 minus c1, the cosine. You can see that. Okay, now here's the part that's I think very interesting. I'm going to show you some things here. Notice that the eigenvalue, if I look at the size of the eigenvalue in absolute value, it's 3, right? This implies a notion of expanding, and this will I hope to illustrate where we can see that when we look at the computer algebra system. Okay, so here it is. What I did, I chose for my system. Let's see if I can find the right one here. Okay, here's what I chose. I have all this stuff. I'm sorry, I was playing around with this. So I found my computer algebra system that I used is this one inside of my on my Mac here. It's called what is it called? Oh, Grapher. And it's very nice if you have a Mac. You can use this, and if you don't, you can use Mathematica, or you can use Maple, or you can use a graphing calculator. But this one's kind of nice because it kind of shows things as they're going. So if you look right here, I just clicked on that. We have our differential equation. It's that the derivative of the vector x. Now they're calling it y. We called it what do we call it? X and x1. They're calling it x and y is equal to a function of x and y. Okay, and I don't know. Well, they gave some initial conditions, but let's just ignore that for the moment. Just look over here at this. But here's our function f. Notice that our function f is 3 times x plus the x component is 3. The one equation is 3x minus 2y. Let me unravel this so I can show you what I mean here. So if you look at our first equation here. Okay, here it is. Yeah, we get, here it is right here. So this is what we're looking at. So there's our f is the thing you're looking at right here. That's the f, minus 3x1 minus 2x2. Well, when we go inside of our grapher, that's represented as minus 3x, then minus 2y, and then the y component is 9x plus 3y. So what you're looking at here, this is the field. These vectors, right, are from Calc 3. This is the you're looking at the gradient of the vector field. You can construct that, And so what you're seeing here is an orbit of a point right here. Let me highlight that. So if I chose, for example, right here, I'm starting off at the point, my initial conditions aren't given, but I'm giving you a starting point of the solution curve here at the point x equals 0. What is it? No, y equals 0, as is indicated right here, right there. So we're taking y equals 0 and x0 at time t equals 0 to be equal to, what is it? What do we have here? X0 in this case is equal to 2. And now watch what's happening. As the differential equation evolves, if I could shrink this a little bit, it'd be really nice. Okay, let me see. Well, what it does is, I don't like that. Let me choose a smaller one. Then it won't go as far away. Let's take x0 equal to 1. Okay? All right, there it shrinks in. So let me traverse the path that the differential equation is, the solution curve is passing. So it's going up this way, right? Then down and up this way. And notice how it comes out a little bit further towards the right than it started. So it will keep expanding, and that's what we mean by expanding. Eventually the trajectory gets larger and larger and larger, and it goes off to far away from the origin. Okay. All right, I want to show you one more thing before exiting. This is a nice, a very nice program applet that a co-author of mine has created. She's at a university called Mercyhurst University in Erie, Pennsylvania, right? And she has this nice thing that she calls the linear transformation applet. And what I've done is, notice I've entered this. This is, notice that just the matrix A in there. So we're not even thinking about differential equations, but you can see a lot of the behavior that is exhibited in differential equations by examining just this applet here. It's a wonderful thing. So here's our linear transformation. And what you're seeing here, you notice how it sort of looks like, has sort of that general principle of what's happening here. And how you should read this is that, for example, if I plug in the point that my little cursor is over, that's the value of the input. If I multiply by a, oops, it moved. If I multiply by a, I actually get that point. All right. So if you you should play with this. I'll give you the address that you can look at this and putz around. I highly recommend it. It's at this one here, this mercyhurst.edu twiddle. I'm not supposed to call it twiddles, but this this transformation page. But I'll show you something else. Just based upon the matrix, you can do these other calculations. Here's the characteristic polynomial of the matrix, which should look very familiar. That's the characteristic polynomial. You'll hear this term over and over and over. That is the determinant of this a minus the identity times lambda set equal to 0. And so the idea is, notice that here we can find our eigenvalues, right? The first eigenvalue and the second value. There's no symmetries, and it's not area preserving, whatever this means. And this is pertaining to a different situation, in an area called linear algebra, which I highly recommend that you study. So anyway, that should wrap it up for the first example. I'll be doing a few more for this section, so I hope that this has helped, and I'll be posting more here today or tomorrow. All right, thank you very much.